So I decided to just skip the second part, since Omega already talked about it extensively. And I think that in this way, we are going to be able to do the third and fourth part in a more leisurely pace. And I think it will be better for us all. So the third part is about classification. Now, I'm going to focus for a while on the projective spaces, and I want to discuss the problem that we want to look at. So there is an immediate problem that is just classify, or perhaps it would be more appropriate to say describe, Codimension 1, foliations on Pn of, let's say, small degree. Let me just remind you that the degree is the number of tangencies with a generic line, and the problem of classification or description can be made more precise, or is related to the problem of describing the irreducible components of the set omega such that omega is integral and the codimension of the singular set of omega is at least 2. Let me just recall you that a section of this line bundle can be explicitly presented as a homogeneous polynomial one form in Cn plus 1, having coefficients of degree d plus 1, and the singular set of the corresponding sections is just the common zeros of these three homogeneous polynomials of degree plus d plus 1. So the problem of describing the reducible components of this algebraic variety, it's an open subset of a projective algebraic variety, boils down to solving these equations. If we write omega concretely as this, where ai, e are constants, which we can think also as variables, then the integrability conditions defines, oh, sorry, here there is also the condition that this form must be annihilated by the Euler vector field. This condition just gives a bunch of quadratic equations on the variables a. So the first question is, well, how far can we go just by forgetting our original problem and look to this bunch of quadratic equations? A naive thought is that, well, since it's just a system of quadratic equations, this should not be very complicated. It should be simple. How simple it should be? Well, let's say that it's far from simple. And the only thing that I can say by only this data is that it can get worse. Indeed, every projective algebraic variety, or algebraic set, you can embed it in some projective space in such a way that it will be defined by quadratic equations. So this fact doesn't seem to be very useful. Anyhow, we have to look for geometric methods to approach this kind of problem. And it's indeed a simple exercise to analyze the case of degree 0. We don't need much more than the definition.
Jorge, to realize any algebraic variety as an intersection of quadratic equations, you probably need to embed in a very high dimensional space.
Sure.
So in this case, could you tell us the dimension, the number of equations, the number of unknowns? Is it really big or not?
I don't have this on the top of my head, but the things are big, but well, it's big. It's quite big. But I don't have it on the top of my head, sorry. Well, but we can do a naive count now, but well. It's really a lot. Some time ago, I asked a friend that was a specialist in computer algebra to take foliations of degree 3 and put on the computer and apply this homotopic method to try to determine the number of reducible components. He said, well, call me next week, I will have an answer. I called him next week, he couldn't write the equations. His computer didn't have enough memory. Already in degree 3, P3. So things are really nasty. But anyway, in degree 0, the things are very complicated, or are very simple. Since we know that at a generic point, I have a leaf passing through it, the natural thing to do is just take a point on that leaf and look for the tangent line. Right? Take a line tangent to this surface. Of course, it has one tangency, but my definition of degree says that if it has one tangency, since the number of tangencies is 0, it has to be contained in the leaf. So if I have a piece of algebraic variety such that the lines tangent to it are contained in it, this is a plane. Now I do the same thing with another point. I will have another plane which will intersect this one in a line. Okay, so now I have to really excuse me by my lack of ability to draw pictures, but I think this, at least this should be clear. And we have two planes intersecting in a line, and it's not very hard to see that when you continue doing that, you're going to get planes containing also this line, because now I can just take a point here and take the line that goes here. Since this is singular, it has a tangent here, so this line must be contained in a leaf. And we have that these foliations are just pencil of hyperplanes. It can get simpler than that. Okay, so degree 1 is more interesting. And one useful idea in this case, which is somehow what we have done here, is to look at the Gauss map of F. What is that? It's just a map from Pn let's say minus the singular set of F, to the dual projective space. So I take a point, a smooth point of our foliation, and map it to the tangent hyperplane. And we have of course, we have two possible behaviors. Either this map is dominant, has dense image, or not. The case that the map, suppose that GF is dominant, then, according to your taste, you can say Bertini or Sard, and take a regular point in the image, look at the pre-image, and see that the pre-image of a regular point will correspond to a hyperplane, a point of the foliation, or a collection of points of the foliation, which are tangents to the corresponding hyperplane. So if H, a regular point of GF, then you can look at the hyperplane corresponding to H in Pn. And I will going to have some points on it which correspond to the two tangencies of the foliation with the point. And being a regular point, it's not hard to verify that this will be a regular point of the foliation. So our foliation, when we restrict to this hyperplane H, will have a local holomorphic first integral by Frobenius theorem. And this will give, if we are, for instance, restricting from P3 on P3, this will give rise to a foliation on P2, which you have centers. You have a singularity, which is non-degenerate because it's a regular point, and which you have a local holomorphic first integral, which is locally of the form x squared plus y squared, which is, in the complex world, the same thing as xy equal constant. So, if you want to study foliations of degree 1 with GF dominant, we have just to understand, let's say by induction, this set.
So why do you say it has a first integral again?
Because I'm really on the regular locus of the foliation on P3. So it has a first integral by classical Frobenius theorem. And I'm just restricting this first integral to a hyperplane. So on P3, this will give this, and then in this case, we are led to consider degree 1 foliations on P2 with a center. Well, for me, a center will be always this, a non-degenerated singularity which has a local first integral of this kind. But this is a simple exercise. Degree 1 foliations on P2 are orbits of one parameter subgroups of out P2. Not necessarily closed, but it's not hard to see that for this set, there are essentially three possible behaviors. One is that we have three invariant lines, and our foliation will be like this. It can or cannot have rational first integral. It all depends on the quotient of eigenvalues at these points. Then you have also another possibility, which is a pencil of line and a quadric tangent to the line. And we also have something with a saddle node. If I'm not mistaken, it leaves two invariant lines. And there is a saddle node here. But that's not important because we only interested in degree of foliation with a center, so this case do not appear. And the only thing that we are going to get is this. A pencil of 2 times a line and a quadric and a conic intersecting transversally. And from this information, it's not hard to show that the same picture happens in P3 or Pn. So if GF is dominant, then our foliation belongs to the rational component that omega r called Raj 1, 2, meaning that it's a pencil of hypersurface of degree 2 and 1 with this one with multiplicity 2. So here I have used that the restriction of the foliation to hyperplane sections will have the same degree, at least over regular points of this map. And I'm going to explore this in the case of non-dominant rational map. So in this case, we are lead to study. We have this. We can restrict this Gauss map to the leaves, and we are lead to study surface, germs of analytic surface, of holomorphic surface on P3, if we restrict to P3, which have degenerated Gauss map. So the study of varieties with degenerated Gauss map was, well, it's very classical. I think as soon as we have varieties, we are lead to study them. And there are very nice works by the Italian school of algebraic geometry, the classical school. And for instance, if I have V, a germ of subvariety of Pn, and the Gauss map of V, a germ of, say, hypersurface. That's what we need. And the Gauss map of V is not of maximal rank, meaning that at the generic point is not of maximal rank. Then the fibers of GF, GV are linear spaces. This is a result due to Segre.
The hypersurface, there is such bright.
No, it's even a germ. Okay. It can be even formal. It's really a local result. It's local projective differential geometry. It's really do the computation if you want. Or you can do by doing duality, but it's really a local result.
Is that from the same field category? Is that from the same field category?
Probably, but I'm not 100% sure, but I think so. I'm not sure.
Just read again, what did you write?
GV is the Gauss map of this hypersurface.
Yeah.
And I'm saying that if it's not of maximal rank at the generic point of V, then the fibers are contained, are union of linear subspaces, are contained in, or the generic fiber. Okay? So the nice thing of this is since that here we have this phenomenon that, well, We don't know a priori if our leaves are algebraic. So they are analytic. But nevertheless, our foliation is algebraic. And if we have this phenomena of non-dominant Gauss map, this result of Segre produced to us a foliation, a subfoliation of our original foliation by linear subspaces. So I'm not doing the quickest proof of that, but I'm preparing the ground for what's coming. So let's again restrict to the case of P3, and we can ask, well, what are foliations by lines? Well, of course, holomorphic foliations. And this is also a classical subject. It can be traced back. There is a classification by Kummer in the, well, long time ago.
It's a French, it's
Monge. And it's related to equations of geometric optics and things like that, which naturally lead to these objects. But Monge have a classification of this. So let me just add Monge to my list. Then we have Kummer. And also, more recently, there are Ran and people for Franchetta, between Kummer and Ran. And even more recently, in the language of foliations, there is a paper, a very nice paper by Cerveau, where you can find the classification that I'm going to describe. So what's the foliation by line? Well, there is an obvious one. You just take a point and look to the lines through that point. Right? Now, we can do also the following construction. You can just take a P1, look
Your foliations are
by lines on P3.
by lines.
By line, really by lines. The first time that I saw this result, for me, the only foliation, for a long time, the only foliation by line that exists was this one, right? It was kind of a surprise to me to see that the things already are mildly interesting on P3, and on P4 already is a wild, wild world.
If you know what holomorphic, I think the Penrose vibration was very
Sure.
but it's not,
This is not
not in
holomorphic,
your,
not in our category. Right. But there is this construction that you take a P1 and look the P2s containing this P1. So the P2s containing this P1 are parameterized by a P1 again. And in each P2, I can just choose a point. Of course, I'm always doing this in the algebraic category. I'm choosing in an algebraic way. And here, I put on this P2 the foliation by lines through that point. And now I turn. And I'm going to have a foliation by lines on P3. Essentially, this thing will draw a curve. That thing will, at the generic point, will intersect only one thing, this P2, right? So the singular locus of this foliation will be something like this P1 and a space curve that has a high tangency, a rational curve, which has a high tangency at some points. But anyhow. Of course, this construction, I'm not assuming that this point is outside the line. It can travel also along the line. It would be very degenerated. But we have this. And there is, of course, the nicest one, which is you take the twisted cubic, which is the curve parameterized by projectively equivalent to this curve, and you look at the secants of this curve. If you look at the secants of this curve, through a generic point of P3, we'll pass only one. This is essentially the fact that when we project this curve to P2, it will be a curve with only one node.
Can you say that? See again the
the foliations, just I take this curve and look at the secants of it. 2 points and take the line joining them. Of course, we always can do this construction, but in general, through a general point, there will be many secants, because when you project this curve through a generic point, it will require a lot of nodes. But this one is the only that requires only one node.
In your example, too, this curve that is the locus of the singular point, could it be something different than a line?
Could be. That's why I said there will be a high tangent here. Because indeed, when you take a P2, it will intersect in 2 points, here and in this tangent point. But this point will be common to everybody. So it will be a curve of degree D, rational, but which will have a tangent of order D minus 1 with this line.
So why it is rational? Why it is rational?
Because it's parameterized by construction. You have a P1 parameterizing the P2 containing it, and okay, we write down the equations and okay. Well, of course, we don't need all that. It's perhaps even a nicer or even deeper result than the classification of foliation of degree 1. But then we have this foliation of degree 1, and we have just to decide in which case we are here. And to decide, it's not very complicated. It's just, you have just to realize that now, if I take a point at the image, since the map is non-dominant, it's not a regular point. Which means that over this, and okay, that's not the point, but let's take a point H in the image. So I'm calling that F on P3, GF, not dominant. And just take the pre-image of this H. So what I'm saying, I know that this will be a union of lines. But what does that mean? That means that my foliation along this line has the tangent plane coinciding with this hyperplane. So when I do the restriction, my one form will acquire singularities along this line, which will make the degree drop, and will be a foliation of degree 0, which we know what it is. And this will be the line which corresponds to the fiber, and we have seen that this foliation by lines, when I take a P2, will have only one line in it. And it's not hard to see that we're on this case. Which means that we have foliation by lines with leaves containing in it. Well, we have this point, the lines through this point, and the leaves of foliation are contained on this. This means that I can recover my foliation from the trace on any P2 outside this. In other words, if I take a P2 outside this point and look at the restriction of the foliation, now a P2 that's not on the image, our foliation will be the fibers of this Gauss map. That will be my leaves of my foliation will be cones over with vertex at these points over the leaves of the foliation on P2. It's easier, these things are easier to think by yourself than to follow the explanation of someone, because at the end they are very, very elementary. But anyway, although, so the conclusion is that on P3, we have two possibilities. Either we are a pullback, a linear pullback from P2, or red 1, 2. And the same thing happens for n greater than 3. We only have to be careful that now we have not not just this dichotomy, dominant or not, but we have all the possibilities, meaning all the possibilities for the dimension of the image. But the things that have not minimal dimension will always be in this irreducible component, and the dimension will be determined by the rank of the quadric that's appearing here. If the quadric is singular, the dimension will be small. Okay. So this is the situation in degree 1. Let's go to degree 2, and this is the very nice result of Dominique Servaux and Alcides Lins Neto. And although they do not phrase in these terms, their proof essentially goes the lines that I've made to do the proof in degree 1. Without mentioning, they look at the Gauss map of the foliation and try to explore this dichotomy. It is dominant or it's not dominant.
So in degree 1 you have 2 components.
2 components.
Of different dimensions.
Of different dimensions.
They intersect.
They do intersect. They do intersect. This is a phenomenon that happens in projective spaces. In projective spaces, the space of foliations is connected. They all intersect. And they all intersect along the linear pullback. This is very easy to see. Just take a P2 contained in your PN, right? And now take an automorphism degenerating to a projection onto this P2. And then you do the pullbacks, and you degenerate everything to this guy. It's not true in other varieties. That's a nice. Even in Fano varieties, it's not true. But anyhow, degree 2 on P3. So the first step is to understand. Let's do in the inverse order. So the first step is to understand foliations with non-dominant Gauss map. And they have this very nice result, which again is not stated like this, is given a formula. You have a formula describing the equation, but then it's easy to see what is happening. And says that if I have F on P3 with degenerate Gauss map, meaning that it's non-dominant, then we are in one of the following cases. A, F is a linear pullback. From P2. Or B, our foliations come from this picture. And the construction is as follows. I am just going to say what are the leaves. So here, you're just going to take a point on this P1, and I'm going to look the cones over this curve, over the singular curve. Right? So this clearly, this variety has degenerated Gauss map, and the fibers of the Gauss map are these lines. Now I'm just going to move the point. At the end, we get a pencil, a foliation which is a pencil, and it has this form. So it is of, let's say, that's the classification. And the funny thing is that on degree 2, they can show that on degree 2, there is only one possibility, will be that foliation by lines will be a line and a conic tangent to it. And I'm going to look at this. And at the end, it will be the same thing as, if I'm not mistaken, the pencil generated by these two hyperplanes. The tangent, I look the tangent of the conic in this plane and consider the plane generated by this tangent and the singular and the axis of that foliation, and the plane contain this conic. This will be one of the elements of the pencil, and the other will be one of these conics, one of these quadrics. So we can deform this to obtain something that is in this, just a generic pencil of quadrics. So this can be deformed. This lies in the irreducible component ret 2, which is just given by pencil of quadrics. Generic element is a generic pencil of quadrics. This one is a very peculiar one, very degenerated one, but there is nothing more. So that's essentially says that the only reducible component in degree 2 whose generic element has degenerated Gauss map is the foliations which are linear pullback from P2. So in all the other cases, we have this picture. We have at least one center. And in this setup, so now with if the Gauss map is non-degenerate, then the restriction to a generic P2 is like that. So we have a foliation of degree 2 on P2 with at least one center. It may have more, but it has at least one. And now, how we can do that? We can also study the space of foliations on P2, which do have a center. It's somehow a more complicated version of our original question. So we got at something that's harder instead of easier. Because at least when you're looking foliations on P3, we had equations, explicit equations, that we could write down or ask a friend to put in the computer. In this case, it works, degree 2. But in P2, we can equate the existence of a center of this type. It's indeed given by algebraic equations, but they are not explicit. This depends, it may be called the Baltin ideal, the Melnikov functions. There are many names for it. And it's a hard problem. But at this point, you can say, read the classics, and Servo and Alcides did. And there is Dulac, who approached this problem. Dulac classified these objects. Indeed, he did not classify these objects because he was not worried about foliations on P2. He was worried about differential equations on C2. And there was a discrepancy. There's a small discrepancy according of degrees, let's say. So Dulac classified these objects, just to be clear, under the assumption that they have an invariant line disjoint from the center. So that's the second main ingredient of Cerveau-Lisneto approach, is this classification of centers. And to be able to use Dulac's result, they proved, using computer algebra, that the existence of a center implies the existence of an invariant line, and they could use Dulac's result. Of course, there are many very nice and very, there are a lot of technical details that has to be filled, but they could essentially translate Dulac's classification to the classification of foliations on P3 and then on Pn.
This part that the center implies line has been simplified.
I will not say that I have not tried. I tried, but I'm not aware of any simplification so far. Okay, so from this we can arrive at the list that Omega mentioned, that there are essentially the linear pullbacks. We have two rational 2-2, rational 1-3, logarithmic 1/4, logarithmic 1² 2, and what they call, and I think one of the sources for the nomenclature is due to Dulac, is the exceptional component, whose generic element is given by the action of the affine group on degree-free polynomials in one variable. As Omega explained it. Okay.
So far, which of these examples have a non-trivial dynamics?
None. None. If you want, this has, it's closed one form, right? That's the worst we can get so far. But I would like to insist, I had a very nice discussion yesterday with Sibony, that the subject here so far is not dynamics. It's more geometry. If you want to see these objects as analogs of generalizations or cousins of varieties, it's natural to understand what we have at the bottom, the things that should be simpler than the other ones. And the point that I was trying to make yesterday is even if there is no dynamics, at least for my personal taste, it involves a lot of nice geometry, nice mathematics. So anyhow. Okay, so we have gone to degree 0, trivially. 1, it was easy. 2, we are very lucky, right? We are aware of the classical literature on the subject, or there were people that were aware, and it happens that they had done what we need. So, okay, there are people nowadays that do this, that work on this problem. Well, let's look at polynomials of degree 3, polynomial vector fields of degree 3, and let's try to compute the irreducible components of the space of these polynomials that do have a center. Next week, there will be a very nice talk about this and how to approach this problem with computer algebra. It will be explained that it's impossible, at least if you just put the equations and try to solve them. You cannot do the first step. You cannot put the equations. You cannot make the equations explicit. There are no computer memory available to write down the equations. And it will be discussed how you can do it, doing reduction modulo P, etc. But that's not my talk. It's a talk by Van Botner or something like that. I'm really very curious about it. But anyhow, we have to look for another proof. We have to look for another methods. So what these foliations of degree 2 have in particular? So let's just recall you that we had this, when we have a foliation on a variety, we had this tangent sheaf. Or even on an arbitrary variety. And if you are going to pursue this analogy between foliations and varieties, this should be like the tangent sheaf, the tangent bundle of my variety. When we do birational geometry, there is a very important, one of the most basic invariants that we look at is to this guy, the canonical bundle of X, which is the determinant of Tx dual. We can do the same thing for foliations. Of course, we can just repeat and write down Kf for the determinant of Tf dual. It will be a line bundle. And a lot of the birational geometry today, of our time, is trying to predict properties of the variety according to numerical properties of these guys. If we have in mind the example of curves, we know that when this guy is positive, we have a hyperbolic curve. When this guy is 0, we have a parabolic curve. And when this guy is negative, we have the sphere. Let's say torus. Of course, we could try to extend this analogy to here. But concretely, what is Kf? At least on the case of foliations of Pn. We can compute it rather easily and see that the canonical bundle of F, Kf, this is notation of Markov, will be nothing more than OPN, degree of F, minus the dimension of F. I'm doing it for arbitrary codimension. So, the case that we were focusing on, degree 2 on P3, are foliations with Kf equals 0. And from this viewpoint, we should not expect hyperbolicity anywhere, right? It's our analog of a torus, let's say. Of course, this is far from true because there are hyperbolicity somewhere. Because we know that foliations of degree 2 on P2 can be ergodic, can have interesting dynamics. There was these, these foliations do have interesting dynamics. But anyhow, even in this, let's say, projective differential geometric approach, we see that this guy appears as an accident. They appear because the Gauss map has non-generic behavior. It has an explanation for the lack or for the presence of complicated dynamics. It's essentially, the thing is not uniformly 0. It's like in this case, if you look to the tangent bundle, it's equal to O minus 1, O 1. So you have the two things, negative and positive curvature. Okay, of course, this can be just blah, blah. No, doesn't necessarily have some content. But what I want to discuss is that it does have content. And the first appearance or the first evidence that these do have contents, is a theorem by Miyaoka. But the version that I will present here is in a more recent version, but with an easier proof, or is due to Bogomolov-McQuillan. And the situation, let's go back to the general situation to try to understand what's happening. And let's just take a foliation now, F, a foliation on projective manifold. I'm going to put a hypothesis, which is the following. I will suppose that there exists a curve away from the singularity of set of F, such that the tangent bundle, because since I'm outside the singular set, the tangent sheaf is a bundle, I will suppose that the tangent bundle of F restricted to C is ample. So if you want, just to have an idea what's happening, ampleness goes in the direction of it's a really strong form of positivity, meaning that when I take the dual, I have a really strong form of negativity. So it should be close to the spheres. And then the conclusion is that F has no dynamics. In the sense that it's a foliation by algebraic subvarieties. Even more, the generic leaf is rationally connected. Okay? I will not prove or discuss the second part, but I will give essentially complete proof in 5 minutes of the first part. It's the original proof by Bogomolov and McQuillan, and I think it's a very, very nice argument. Indeed, they prove something stronger. They don't have to impose this. But anyway, these are technicalities. But the idea is the following. Well, let's just rephrase for the analysts in the audience what this means. It means that if I look at this bundle over C, then a neighborhood of the zero section of is pseudo-concave? Pseudo-concave, Marco? Right? But anyhow, how the proof goes? The proof is the following. I look, this is my favorite picture. I look at the curve C and the manifold X, right? I look the two things together. And now I look the embedding of C into X. I look at the graph of it. So I have a kind of diagonal here, right? And we have this now a projection from the product to here with fibers are just X. Now, at each point, of our curve, I look at the leaf through that point. And I put a copy of it here. I put a copy of the leaf through this point in this copy of X. Okay? And I can do this for all points. So in this way, I will construct a variety of dimensions. See, if X has dimension n, this will have dimension n also, which contains this diagonal, and such that the trace of our leaves can be recovered as the levels of the projection from Y to C. Because over a point of C, the only thing that I've put here is the leaf. Right? So somehow, in this neighborhood, our foliation is given by the level sets of this projection. Of course, this variety can be very complicated. But why this construction is interesting? Why the construction is the following. I put this diagonal, right? Now, at each point, I will put the germ of leaf through that point in this fiber, in the corresponding fiber. So that's why.
Why do you call that a variety?
It's not algebraic. It's an analytic variety. If you do this like that, it's very, very transcendental. If you start with the arbitrary foliation, it's very, very transcendental. But the nice thing of this construction, that it translates a problem about the tangent sheaf of this foliation to a problem about the normal bundle of this, the tangent sheaf restricted to C, about the normal bundle along the diagonal. So if we do the obvious identification of the diagonal with C, then the normal bundle of delta in Y is the tangent sheaf restricted to C. Right? It's a diagonal, and the foliation is given by the fibers of the projection. And now, the point is that since the tangent sheaf is ample, this guy is ample, this neighborhood is, if you are an analyst, pseudo-concave, or if you prefer algebra, even if you look at a formal neighborhood, there are results in the analytic category by Andreotti and results in the algebraic category by Hartshorne that says that the degree of transcendence of the field of meromorphic functions of this guy is at most its dimension. On the other hand, since it's analytic subvariety of a projective variety, C times X, it's at least its dimension, the degree of transcendence over C of the field of meromorphic function. So we conclude that it's equal to the dimension, which means, in other words, that this guy is a piece of algebraic variety. So we have this, the ampleness implies the hypothesis that ampleness implies that degree of transcendence over C of the field of meromorphic functions on Y is bounded by the dimension of Y. This is Andreotti or Hartshorne, as you want. And on the other hand, since Y is contained in C times X, the degree of transcendence of C over Cy thank you. It's at least the dimension. Because I have a bunch of meromorphic functions here. I can take the dimension of 5 meromorphic functions that have kernel that have differential transversal at a given point. We can get it. But then,
So what is the hypothesis to have the Andreotti or Hatch?
ampleness. Andreotti is pseudo-concave neighborhood.
Any pseudo-concave neighborhood.
You have this.
Any pseudo-concave manifold.
Any pseudo-concave manifold, yeah. And Hartshorne is this. You have a subvariety with ample normal bundle. The proof of, I don't understand the proof of Andreotti, I've never read it. The proof of Hartshorne can be explained in 5 minutes. It's really simple. But anyhow, we have this, so at the end we conclude that they are equal. But if they are equal, this means that it's an algebraic variety. In other words, the degree of transcendence, that Y is a piece of algebraic variety. And because this I will get the closure here. On the Zariski closure will be an algebraic subvariety of X times C. And the leaves will be the level sets of a rational projection, of a holomorphic projection. So they are algebraic. And that's it. To prove the second part, you have to do the now standard technique of Mori bend and break. But already to see that negativity of the canonical bundle implies no dynamics, that's enough.
So I may be slow, but I did not understand the last step. So Y is a piece of an algebraic variety. So what?
How do we recover the leaves? So the local picture is that the leaves are fibers of this projection.
Is this projection algebraic?
Yeah, it's just the X times C I project to C.
Algebraic in the structure that makes Y algebraic?
Y is algebraic as a subvariety. You can just take the Zariski closure and we will have the same dimension as Y.
So this is what I don't understand. When you said Y is algebraic, you mean Y has some algebraic structure. Why is it algebraic?
Ah, no, it's just that the claim is that if I take the Zariski closure of Y, the dimension is equal to the dimension of Y.
Zariski closure
In X cross C, I'm C. Okay, and this is really, I just restrict the meromorphic functions on X cross C and see that they will satisfy some. Okay, and then I can recover the leaves as just projections to. And that's a really nice point because we are translating something about the geometry of the foliation to something about the geometry of this variety Y. Of course, we can consider Y for any foliation in any curve. And it's in this direction that Marco constructs his covering tubes and things like that. But I will stop here.